A heap must be a complete binary tree, meaning every single level fills perfectly from left to right, leaving absolutely zero gaps. This strict gapless structure creates a hard mathematical pattern. To find any left child, just take the parent's index, multiply by 2, and add 1. Apply that to our root at 0. 0 times 2 plus 1 is 1. There's the left child. And 0 times 2 plus 2 is 2. That's the right child. The physical branches are never actually saved in memory. They're calculated instantly just by reading the array positions. How does a heap data structure process incoming data so quickly? Because perfectly sorting a standard list every time new data arrives is incredibly slow. Imagine a busy hospital triage system that must always treat the most critical patient next. A heap solves this using a binary tree, placing the absolute highest priority number at the very top. It enforces one strict vertical rule. Every parent node must be greater than or equal to its children. This guarantees the largest number always rises up. This structure is called a max heap. But look horizontally across the siblings. They have absolutely no order relative to each other. From left to right, the rows look completely chaotic. And that messiness is the heap's true superpower. By only enforcing that weak vertical rule, it skips the heavy cost of full sorting. This allows new data to enter in a fraction of the time. And if you flip the rule, making parents less than or equal to their children, you create a min heap, instantly moving the lowest number to the root. So when that chaotic emergency room suddenly fills up with dozens of new patient arrivals, the triage system doesn't freeze up. It instantly bumps the most critical patient to the very top, ready for the doctor.
It perfectly balances lightning-fast access with incredibly efficient inserts and deletes.
Priority queues are the coolest application here, flawlessly managing task schedulers and complex, event-driven simulations. The whole goal here is making sure your system processes the absolute most urgent item next. In fact, your computer's OS schedulers and massive server load balancers rely entirely on heaps for job scheduling.
Moving to graph algorithms. Dijkstra's and Prim's use min heaps to constantly snatch up the absolute cheapest edge.
Need the top k largest elements? Just maintain a heap of size k. No need to sort everything.
This perfectly shows why heap sort is such a fantastic, in-place, O(n) log n sorting algorithm.
Heaps even make Huffman coding super efficient, letting you easily merge the two lowest frequency nodes over and over. So without heaps effortlessly managing these priorities behind the scenes, how painfully slow would your computer really be?